So we're still on that topic, quantitative composition. Today we've specified, we said last time instead of substances, we've specified of compounds. Because an element just has one thing, it's just itself. But then compounds are made up of different elements. So that's why we struggle so much on finding the composition of the compound. So the first one is the percent composition of a compound. This is very simple. This is very simple. So everywhere you see percent, so for that one, like for a compound, if it's percent by mass, which is usually the case, sometimes as I told you in chemistry, we even say percent by weight. So when someone says percent by mass of an element or of a compound, percent by mass of a compound, that refers to parts by mass of an element in the compound per 100 parts by mass of the compound itself. So that's what we mean when we say it means parts per 100 parts. So parts per 100 parts, meaning the entire compound is 100. Then your element is a part of the 100. So this is like a fraction, a decimal fraction, and we always multiply by 100. So you always have to remember that. So the percent composition of a compound is the mass percent of each element in the compound. So that's the most important part. You must know the molar mass, e.g., like for water, you must know that the mass of the entire water, the molar mass, is 2 because hydrogen is 1. So 2 times 1 plus 16, so it will be 18. So this is the same. The beauty with the percent composition of compounds is that we refer to the law of definite composition. I'm sure you remember that one. So the percent, like for water, ngawaishuba fi percent ya water. iPhone phone na mic na ya iPhone. So that's the thing. So it's law of definite composition. So if someone asks you to say find the percent composition of 2 kg water, and then some other person was asking you find the percent composition of say 200 grams water, the answer is the percentages will be the same regardless of the size of the sample that you have taken. So that's the way it is. So there are 2 ways of calculating percent. It doesn't really make sense why, but when you start calculating empirical formula, that's when you realize that the experimental data is also very useful. It's also very useful. So this is the case now. So you must know, you get the percentages if you know the formula, or someone will give you data from an experiment to say this and this reacted, and that's the case. So for that one, from the formula, you just calculate the molar mass, then you calculate the molar mass of each element. Wasanga yonse total mass of an element. Then the total mass of the element over the molar mass, when you multiply times 100, what you get is percent of the element. So we can give you even percent stock per percent. We ask you for the total mass of the element. You should just know to change the subject of the formula. That's key for science. It's very key. Not sometimes they can give you the percent, they even give you the total mass of the element, then they ask you for the molar mass. It's very acceptable. So you must know that these things are useful differently. So now, the first two examples, this one and this one, are looking at something that contains sodium, that contain chlorine, the chloride ion. So now, both potassium chloride and sodium chloride contain the chloride ion. So there's a statement that is used with reference to this. So the mass of the sodium is 22.99 grams. The mass of the chlorine, the chloride ion, is 34.45 grams. Then the total is 58.44 grams, which is 58.45 approximately there. So that's a molar mass. So to calculate the percent, this is what you do. For the sodium, 29 point chan over the 9. Very boring if in the fund. That's why I'm now. But call me funda feka ismara na titam uturondoroela. So 22.99 over 58.44 times 100, you get that percent. Then for the chloride ion, you get the other percent. The idea of percentages is that they should add up to 100. They should always add up to 100. Mwabale sanga 99.999 mule puturafi. When you round off that 99.99, it's also just 100. Mwabale? So that's the scenario. For the second one, calculate the percent composition of potassium chloride. You do the same. Potassium is 39.1 grams. Then chloride ion is the same mass. Those are the percentages. So now the statement is that when you look at these two, the molar masses, if you have one more this and one more that, it means you also have one more chlorine, except the masses of the other components are the ones that are tilting the percent by mass differently. So percent by mass can be different, but the moles that you're talking about are just still the same. Because chlorine, one more of chlorine, one more of sodium chloride and one more of potassium chloride, both contain one more of chloride ions. If you wrote the ionic equation, I'm sure you know. So despite it being one more of chlorine, their masses are different. Their percentages by mass are different because of the other component, which is the sodium and the potassium. So always that, meaning even if you have the same molar amount, when you have different compounds, you find that will give you different percentages. It's just so that you don't get used. So there's this comparison now there to say the percentages, the masses are different, but the moles are the same of the chlorine. The moles are the same for the chlorine because it's one more chlorine, also one more chlorine there, one more chloride. That is the case. So that is very acceptable. So if someone asks you how many moles, you will say one more chlorine, one more of the chloride ions. But what masses? The masses are different. So those are the scenarios. And remember that one more, the molar amount also refers to the number of particles, because the Avogadro's number is related to one mole. I'm sure you know that. So those are the scenarios. Okay, the idea is that in both there's 35.5, there's 35.45 grams, which is the molar mass of chlorine. So that is the scenario. You've performed very well, guys, with my percent, because these are supposed to be free marks. If someone asks you for this, these are supposed to be free marks. You must enjoy them. So you have potassium sulfate. So you remember that you have two potassiums, so it's 2 times 39.1 plus 1 sulfur. That's where this mass is coming from. And then these are 4. So the total masses for potassium is 2 times this, which is 78.2. Then for oxygen is 4 times 16, which is 64. Then the total mass of everything when you add is 174.3. So meaning it's even acceptable that you find the first two, then to find the last one, you even just subtract from 100 the two. Okay, when you add these, they should give you the total of approximately 100. 99.999 is approximately 100. So those are the scenarios. I loved your work, guys. Now wino sana. You have solved these ones. These calcium, remember, is 40. Then there are 2 nitrogens there because there's a 2 outside there, and 6 oxygens. Let's see the first person to attempt. 2 and 6. This nishasangana okusanga omuntu 164. Then the total is there. Richard, keep up. Also Janet, keep up. Namusanga fe buno bwino tumanani. Despite twam G10, don't you go mkuidombokcha ninsanga sana delo. Twam grade 10. But you have done very well. So you have found this. Even this one, the second one, very straightforward because there are no brackets. You guys are the best. So when we look at all your work there, Richard was still working. You must keep up. All right, Jonathan was trying out this one. If the working is very acceptable, except have you noted that the chromium, some of you in your periodic tables, the chromium is giving you something else, but we'll still stick to 52. So if your periodic table says 52 for chromium or 51 point something, then you're okay. All of you guys have done so splendid a job. Edward, good work, except ka oxygen taturembaka no tata ba Edward nadimi kanya ba Edward namutemosana efe ukulembo tuma ka owaka no. It's supposed to be a big oxygen. Otherwise, all of you, Irene, you compare the notes. The first two that I put there were very accurate. So those are the scenarios. So this one was potassium sulfate, and that's the expectation. From experimental data, there's just a mention of the elements. There's just a mention of the elements. So we have that. So here nakubonvya fifth combine. So say they've said 1.63 grams of zinc plus 0.4 grams of O2. Zinc oxide is just ZO. But the O2 it changes pakayaba off here, like when they combine with that one. So it doesn't matter whether it's O2 or whatever, the mass of oxygen that we have. Even this diatomic oxygen is oxygen. So the total mass is 2.03. So you don't look at the formulas per se if you're looking at it from experimental data. As I've said, we have O2, and yet the formula, zinc oxide, it's ZO. So to divide the monthly if you say no, you just put the values that you've been given, oxygen and zinc. They react completely to form zinc oxide. So all the O2 goes to form the oxygen in the oxide. So what you do there is just add them. 2.03 wakwata. Then to get the percentages for zinc, mass ya zinc over the total times 100, 80.3%. Then inayo over the total times 100, it should be watch a book but when you do your notes properly, you will find. So I also gave you something. Let me see if someone attempted this one. Yeah, none. Okay, we're looking for someone who has done this one. Okay, Janet. So that's the way it is. You just add them as is. if those are the masses given, those are the ones you use. So like that. I think she's done a splendid job also now. You just add them as they've been given. It doesn't matter whether in the formula it becomes CO3. That is the key. I'm sure you are following like that. So, but period 13.43 and 53.18. So you just add them. It doesn't matter whether it's CO2, but formula part is CO3. You just add them, then you divide and multiply by 100. So what Janet has done is very splendid also. So now, the most key things now, of what today is multiple choice to the but if it's a number mukusova, ni that empirical formula na molecular formula. The empirical formula gives the smallest whole number ratios of the atoms. So it's called the simplest formula. So the formula that gives the smallest whole number ratios of the atoms present in a compound. The smallest whole number ratio, meaning you do it, you always find it in the lowest terms. That one is the empirical formula. For ionic substances, ionic compounds, almost always the formula is empirical. Because if you remember, so when you exchange the charges, we divide the structure to find it in its lowest terms. So the problem comes in when we have covalent compounds. Because if you remember, like for hydrocarbons, when you remember in your grade 12, you used to say C2H4, C3H6, those are acceptable. Like so that those ones, the empirical formula and the molecular formula becomes very distinct. But for the ionic compounds, the empirical formula and the molecular formula are almost always the same. They are almost always the same. So those are the things. So there's a mention now there to say we can establish empirical formula because one, individual atoms in a compound are combined in all number ratios. So there's almost a factor. If there's a factor there, it can easily be dealt with because always talk about H2.5. We don't do fractions there. Then the elements are combined. Where is the number 2? Each element has a specific atomic mass. So that's the way it is. So there's a rule there. You can go and read. So in empirical formula, we write them as X, B, Y. So those ones should be small numbers. That should be the case. So those are the scenarios. The rules are those to find empirical formula. So if you've been given percentages, you assume that the percent is 100 grams. If you've been given masses, you add the total, or you just deal with the total, yes, so that you can find the moles. If you've been given masses, you just go direct to moles. Because the idea next is to convert each percent. So the percent that you've been given there, you divide it by the molar mass to get the moles. Then you divide each moles on the sides like that, so that you can get them in small number ratios. So now, if after dividing, you find, say, a ratio 1 to 1.5. Now, guys, the only ones that are acceptable is when you find something like 0.1, 2.1, 2.0 shan. Those ones are acceptable. Once you go beyond 2.1, it's not very advisable that you round off. You must find a factor that will make everything a whole number. Like if you have 1 to 1.5, I'll explain this with an example. That's why I put an example there, because so if you have 1 to 1.5, you don't just say 1 to 2. Remember, guys, you factor everything here and multiply both 1 and 1.5 by 2. 1 and 1.5 by 2. I'll give you the factors the next time on Wednesday. I'll give you the factors to say if it's point this. So if it's 0.5, you multiply by 2. So what you get will be 2 to 3. What you get will be 2 to 3. So that is the case. Then for the molecular formula, the simple thing is just to get a molecular formula, guys, you must know the molar mass of the entire substance. Then you divide over the mass of the empirical formula. And that's a factor that you multiply with. So we'll also do that when we come on Wednesday. So on empirical and molecular formula and empirical formula, for especially for covalent compounds, is very different. Look at benzene and ethene. In fact, this ethine, this acetylene. What you get, you find that when you look at them, C2H2, C6H6, percentages are the same. When the empirical formula is the same, the percentages by mass are also definitely the same. But these are different compounds. This one has a triple bond, the other one has a ring structure. So you can't say they are the same. So that's why it is important for you to know how to find the molecular formula. So this is how I was saying you should find the factor n, which multiplies everything. And then for the factor n, you write it in this form. You say brackets HF, open brackets n. This n, how do you get it? It's molar mass of the formula over the mass of the empirical formula. So this is the scenario there. So the example for empirical formula is there. I wished I wrote it in pen. So you have 11.19% hydrogen and 88.79% oxygen. When you add them, they don't even give you 100%. But then they'll give you 99.9998, so somewhere there, which is approximately 100. So you assume 100. So meaning you just assume that these percentages are also grams. So you say what is the 11.19 divided by what is the molar mass for hydrogen? It's 1. So it's 11.1. 1.008. So it's 11.1. Then the other one is 88.79. You divide over 16. It gives you this one. Then you look at which one is smaller there. You will see that the 5.549 is smaller. You divide it throughout in itself and under the other one. So what you get there, the simplest ratio will be 2 to 1. So what you get is H2O. Richard, do you have something to say? Richard? Humphrey?
Yes, Mr. Gunn.
Yes.
On the example empirical formula, Mudisa first, we are not understanding what you're saying.
I was expecting that you knew these things from your grade 12. Sorry. I was saying if you've been given, the rules were there. If you have 11.19%, you assume it as 11.19 grams. Then 88.79%, you also assume it as 88.79 grams. The percentages, you just add the gram, you remove the percentages for you to easily find the empirical formula. Then each gram now, 11.19 and 88.79, you divide them by the molar masses of the things that you have. Hydrogen molar mass is 1.008. Oxygen, the molar mass is 16. Then you divide. So you get the moles. When you divide 11.19, you divide over 1.008, you get 11.1 more. Also, oxygen, when you divide over the molar mass for oxygen on your periodic table, which is 16, you get 5.549 more of oxygen. Then the smaller one is 5.549. Kaina bakalembana kano that text to remember formula yaso. It should be in all numbers. So you divide E no, you divide it over itself, also over the 11.19. Then what you get when you divide a number papangele division, 11.1 divide 5.549 is approximately 2. Then for the oxygen, 5.549 divide 5.549 ni 1. So the mole ratio is 2 to 1. I don't know. Guys, in the first na papasa. An empirical formula. I'm free.
Mr. Kandos, I have now understood.
Guys, tuma empirical formula to apa J10 atwaresha ina ukwa mufunda wa G9 watabafishi. Guys, this is empirical formula. Then I put up this formula now. There now it's mass. So the key is to find moles for empirical formula. So upper we have iron sulfide. You can even just be given if it was percent. But iron sulfide. Iron sulfide contains 40 grams iron. Or 40% iron. You should know that the other one is sulfur. Because it's iron sulfide. So if you want to get the other, if you've been given, say, iron sulfide is formed by using 40% iron, it means the other one, the sulfur, you just subtract 100 minus 40. Okay, percentages, they should add up to 100. So Emma setting drip shaft, sometimes we also drip shaft iron sulfide contains 70% iron. Find the empirical formula. No need to alasanga shani nga imbi. All but percentages should add up to 100. So if the one is 70%, the other one should be 100 minus 70, which is 30. So if you over sharp sana okupishamo pencil, that's why tuchudila kumiti magai. Kale fya potawa ishiba because ta opishamo pencil. Fya dipwaka de umuntu adi kusamba mwadi bitana move on. Aleli na lunch somewhere else. You adi sharafi wa no. Akachinja kanjo umuntu alichinja kale ali kuchinja amano. So those are the scenarios. So now for this one, 2.233 grams iron, 1.926 grams. There's nothing like assuming them to be grams. We've already been given grams. So for these ones, you go direct to find the moles. You go direct to find our team, the moles. So you find the molar mass for iron, which is 55.85. Also the molar mass for sulfur, which is 2.07. So you find the moles. Here iron, you do 2.233 grams over 55 over 55.85. Also 1.926 grams over 32.07. So these are the ones. Then when you divide them into each other, what you get is that ratio. 1.00 and 1.502. For these ones, you don't just round off to say even 1 to 2. You don't. There, you multiply both by a factor of 2. Why? Because this is when it will become a proper whole number. If you have 1.5, if you have 0.5, I'll send. Promise if you have whatever it is that I promised last time, I promise paper, then I'll post on WhatsApp. It's a promise. Because na promise ama triangles in shibiki yo. So those are the things. So that I don't forget, I'll do it just today. If into nibwangu. Kama promises in our panga yakale. So you multiply by factors, a factor of 2. If you have 0.5. If you know so well, guys, 1 divided by 2 is 0.5. That's why we're using the factor of 2. So if you do 1 divided by 3, you find 0.333333. So I'm a 333 somewhere. You multiply everything by 3. 1 divided by 4 is 0.25. So I'm going to put 0.25 somewhere. You don't just round off, you multiply by 4. If you do 1 divided by 5, it's 0.2. So it means for that one, if you have 0.2, you multiply everything by 5. The only thing you round off, unless you quote a 0.1, nangu, anything less, 0.00 something, or maximum 0.1. But otherwise, in all cases, you must find the factor if it's greater than 0.1. So when it's multiplied by, it was multiplied by 2 everywhere. It was na Fe2S3, which is iron 3 sulfide. May someone conclude the lesson in 5 minutes? May someone conclude the lesson in 5 minutes, guys? Continue working hard. Avena Irene, continue working hard. Ezekiel, Amos, keep being busy. But Irene can order to them back on mile. We don't write a small O. Irene Milambo, we don't write that. So those are the same. Chongo.
Yes. The network was breaking. I was not clear on the last part. Is it always we should multiply by 2 when we find those small numbers?
We multiply by 2 because the other number at the 0.5. And I was explaining a pin why we multiplied by 2, because if you know so well, 1 divided by 2 is 0.5. So if there's a 0.5 somewhere at the end, you multiply by 2. Then if you do, calculator, if you do 1 divided by 3, you get 0.333. There is what calculator. So we get 0.3 and 0.33. You multiply everything by 3. If you've seen, we multiplied the 1, we also multiplied the 1.5. So that we ended with 2 and 3. These are the ones that are acceptable. These ones are now acceptable to be used. Then if you go to 4, 1 divided by 4 is 2.5. So if one of them is a whole number property, then the other one ends with 0.25. Then you multiply everything by 4. 1 divided by 5 is 0.2. So if you have a 0.2 somewhere, say 3.2, then you could 5, you multiply everything by 5, because 1 divided by 5 is 0.2. Are you getting some, Mr. Chongo?
Yes, sir.
Yeah. So it's not always that you should do but for your level, deliberately the 0.5 ilasangwa sana, because kaina efundwa n'okufundwa abenkaya abantu nga wasalira bet 0.25 despite okulondolola bakesalanda okutira atufundire ya 0.5 alete ya 0.2 kandulo mwayimonate. So I'll explain. That's why I said I'll write on a piece of paper, screenshot, and send it to your WhatsApp, so that it improves your understanding, guys. Very sharp question. You have very sharp questions, guys. You can go and read through molecular formula. I want you to go and read through there as well. Anything else, friends? We have 2 minutes. So simply what we are doing to find the number of moles is to say mass over molar mass. Moles equals mass over what? Molar mass. Just that the book I'm using, they're emphasizing on converting so that the units cancel. But we are simply just doing mass given over molar mass. I put what percentage But perife grams, you just use them as grams like that. Only when you have a percentage, that's when you start struggling with converting them to grams. Then I want you to go and read further on the molecular formula. So when we come to look at them, because the entire session on Wednesday will be a tutorial on this. So I'll look for as many questions as possible so that you perfect your skill, you guys. You're learning from home. So we want you to be the best ones yet. Bachongo macha watu mande kwa kina tumbi. Mr. Chongo. Mr.
Yes,
Chongo.
sir.
Yes.
Yes, sir.
Huh?
I'm clear on that one. The one you are just from explaining.
All right, cheers, sir. I'm happy when you are clear because
Okay.
it shows that I'm doing my best. So these are the scenarios. Go and go through that formula. I want you to go and do molecular formula again because we haven't done any example there. I want you to be a step ahead even as we are doing the examples on Wednesday. So about my job is to go in Google and Google as many questions as possible. Even you do the same. Progressive class, though not very participatory, but I've enjoyed to explain these